And welcome to GER Hub. In today's class, we shall be discussing the laws of indices. That is proving the laws of indices. So, if you haven't subscribed to my channel, please go and click the subscribe button. Thank you for supporting this channel all the while. If you are somebody who is already subscribed to the channel, thank you very much. So, we are looking at proving the laws of indices. This will be my second class on indices. So, please let's begin. So, proving the laws of indices is what this video is all about. For the laws of indices and what indices is all about, I had made that known in my first class on indices. So this is what we shall be doing. I shall be taking the laws we discussed one after the other. So the first law we discussed was the addition law. The addition law of powers. So I told you in that class that please take note that these laws, the names of these laws, are not as important as the meaning of these laws. So please let us hold on to the meaning. Now, in some textbooks or in some materials, they may call this law a different name, such as the multiplication law of indices. However, I'll be calling it in my video and in my class addition law of power. So let's see what this law is all about. So the law states that a raised to power x times a raised to power y is equal to a raised to power x plus y. Now please take note that this law simply tells you that if you multiply two numbers in index form such that the bases are the same, a and a, the bases are the same, x and y are two different powers, then the law demands that the powers be added in that base. So what we are going to be looking at is proving this law. So how do we go about doing that? We shall start with recalling that a raised to power x can be written as a raised to power a times a times ellipsis a for x number of times. Okay, so remember in my last class I told you that if you have a number in index form such as a raised to power x, it means a multiplying itself x times, and that goes for y also, that y will be multiplying itself a will be multiplying itself y times. Okay, so if we go by this, then it means that we can now go through the process that a raised to power x times a raised to power y is the same as a times a times a times ellipsis a, the multiplication continues for x times, okay, times a times a times a times ellipsis times a y number of times. Okay, so that is what it will mean. Now this goes to show you that if you look at this set of a's multiplying this set of a's, this is still a multiplication. As such, they all will put together be in multiplication. So when you multiply all of them, it ends up giving you a times ellipsis a x plus y times. Okay, so if you merge all the a's, okay, welcome Alvan Ekbang Danya from information system. Thank you very much. I thought there was no one online. I had to start this class 1 hour late, so thank you very much for joining. Nonetheless, I'm grateful. So now if you multiply, we are trying to prove the laws of indices starting with this law. I hope it is clear. Please, if the video is clear from your end, could you just let me know? Thank you very much. So a raised to power x times a raised to power y is equal to a raised to power x plus y, and I'm saying in expanded form a raised to power x can be written as a times a times a times ellipsis a. Ellipsis means the multiplication continues to the last a, and there are x a's. Okay, so in that multiplication, it also goes for a raised to power y, that there are y a's in that multiplication. So now if you now multiply a raised to power x by a raised to power y, it is going to give you a times a times a times a x times multiplied by a times a times a times a y times. Okay, Guys, please, could you just let me know? Olga Joe, welcome, information system. Kindly let me know if this video is clear on your part. I really want to know. Thank you very much. Now, if you merge all the a's in multiplication, you end up realizing that you have actually multiplied a by itself x plus y times. And that would mean that if you multiply a by itself x plus y times using a similar notation, then this would mean a raised to power x plus y. If a raised to power x means multiplying a by itself x times. Okay, I think the video is now clear. So, because let me now re-explain, please. So we are proving the laws of indices for those of you just joining at this point in time or watching from any part of the world. Sorry, the network was somehow bad or terrible at the beginning of this video, so I have to really recap. So proving the laws of indices is my second class on indices. The first law we are going to be proving in this class is the addition law of powers. And I'm saying that please take note that the name or the name of this law is important, but not as important as the meaning of this law. So what we are doing is trying to prove that this law is true, meaning that we are proving that the left hand side is equal to the right hand side. Now I started with saying that a raised to power x can be written in expanded form as a multiplying itself x times, and a raised to power y can be written as a multiplying itself y times. Now if that is the case, by that notation, it means that a raised to power x times a raised to power y will be a multiplying itself x times a multiplying itself y times. And if you put all the a's together in that multiplication, it will mean a multiplying itself x plus y times, and that will give you a raised to power x plus y, which means that the law is true. Proving from the left hand side to the right hand side, it is true. Now let's go over to the second law. So this class is all about proving the laws of indices that we had taken in the first class. So if you haven't watched that video in the first class, please go over it again. It's in my channel. Please go back to that video, or I could put the link in the description below. So please, let's go to the subtraction law of indices, or the subtraction law of power. So the subtraction law. Okay, I came late, and where I'm now is a lot kind of noisy. Okay, you will watch it later. Thank you very much. Thank you very much. So subtraction law of powers. Okay, so over when you are done with when you are done with where you are, you can watch this video all over again from the start. So now we want to prove this second law. The second law says a raised to power x divided by a raised to power y is equal to a raised to power x minus y. Okay, now please take note, in this law the condition is that x is greater than y. Okay, x, the number x, whatever it is greater than y. So holding on to that, we know now that a raised to power x divided by a raised to power y could be written in this manner: a raised to power x all over a raised to power y. Okay, so that's the first thing I'm going to do. Now the second thing I'm going to do is this. I'm going to use the expanded notation for a raised to power x. So I'm going to write a times ellipsis 3 dots times a x times, okay, in my numerator. Then I'm going to write a times times ellipsis a y times in my denominator. Okay, now please take note, provided the xa's above, if there are xa's in the numerator but ya's in the denominator, so I'm going to write here, if x is greater than y, that is, it means that the number of a's in the numerator will be greater than the number of a's in the denominator, such that you can actually separate it in this manner: a times ellipsis a, since we don't know how many a's are there, that is x times, but we don't know what x is. So I can actually separate in this manner, such that I would have this one group. I'll have one group I call x minus y times. So if you separate it, you will have one group called x minus y times, and you have another group called y times. Now, why am I doing this for the numerator, guys? It is because the number of a's in the numerator is greater than the number of a's in the denominator. There are ya's in the denominator, so I have a times a times ellipsis a, okay, in my denominator. So I have YAs in my denominator. Now, if you separate the numerator, since the XAs in the numerator are greater than the YAs in the denominator, it means you can actually extract YAs. It means that you can actually extract YAs from the numerator and you'll be left with X minus YAs in the numerator. So once you get that done, that means, thank you very much, Charlie Okon, thank you very much. So once you get that done, it means that you can now cancel the YAs in the numerator and cancel the YAs in the denominator, and you will be left with a remnant of A times A times A times ellipsis A, that is X minus Y times in the denominator. And this, by the same notation we had used earlier on, will be equal to X raised to power X, A raised to power X minus Y. Okay, so for clarity's sake, let's just quickly repeat that before we move on to the next. We are now looking at the subtraction law of. Please, the emphasis is not on the name of this law. The emphasis is on the meaning of this law. So A raised to power X plus A raised to power Y divided by A raised to power Y rather is equal to power X minus Y. And I'm saying that provided X is greater than Y, this law is true. This law is only true when X, whatever the value is greater than Y. Now that means that you can write A raised to power X divided by A raised to power Y as A raised to power X all over A raised to power Y. You can do that, and once you get that done, you could now bring the expanded notation for each of them in the numerator and denominator in. So A raised to power X means multiplying A by itself X times, and I'll put that in my numerator. A raised to power Y means multiplying A by itself Y times, I'll put that in my denominator. So I will now put this condition that this is true if X is greater than Y. Now, because X is greater than Y is our assumption, it means that in these A's, the XA's in the numerator, I can actually remove YA's from the XA's in the numerator since XA's are greater than YA's, okay? And if I do that, it means separating the A's in the numerator into two groups, X minus Y times and Y times can be separated, okay? So if you separate the A's in the numerator into two groups, extracting from them YA's, leaving you with X minus YA's, then the YA's in the numerator you've extracted will cancel the YA's in the denominator, leaving you with the X minus YA's in the numerator, and that would mean writing it in this manner, A raised to power X minus Y. I don't know why, or I don't know how terrible the network is, but I hope it is clear on your side. That being said, let's go over to the zero index law, the law of zero index, which was my third law if you are following the class, okay? So the law of zero index. So I called this in my first class on indices for this semester, I called it the zero index law. So what was the law all about? It says A raised to power 0 is equal to 1. That was the law. So how do we prove that this law is true? For you to prove that this law is true, you start with saying that 0 is actually, A raised to power 0 is the same as writing A raised to power X minus X. Anything minus itself will give you 0. So I will start with proving this law by saying A raised to power 0 is equal to A raised to power X minus X. Once that is done, I would now recall that by the law of subtraction we've just taken, by that law, this will be A raised to power X divided by A raised to power X, according to the law of subtraction we've just taken. Now, this means also that A raised to power X over A raised to power X can cancel to give you 1. So this law is as simple as that to prove. You can prove this law as simple as that. Now, let's move over to the fourth law. Let's move over to the fourth law. The fourth law in my lecture was on the unity law. I called it the unity law, and I've told you, please take note, it may not be the unity law in the textbook you read, but I'm calling it the unity law. So this law says that a raised to the power 1 is equal to a. Okay? Now, how would you prove this law from left to right? I'm going to start with a raised to the power 1 is the same as writing a raised to the power x minus, in bracket, x minus 1. Okay? So what have I just done? X minus 1 will give you 1, so we've done nothing wrong. X minus 1 is just like saying 5 minus 4. 5 minus 4 is the same thing as x minus x1 is the same thing as saying 5 minus 4, because 5 minus 4 in this case is 1 less than 5, and that can be written as 5 minus 1. So if you do that, this 5 minus 4 will give you 1, and so will this give you. That is the technique I'm going to be using. So what I'm going to do next in the subtraction law by saying this is the same as x minus 1. Okay, so if you followed what I've been doing previously, even the beginning of this video, please go over it again. Okay, thank you very much. Hashtag unity law. Now I'm going to do this. I'm going to write what you have here in this manner. So I've done nothing wrong. Please follow the logic. So what does it mean? It means that x is greater than x minus 1 just by 1. Okay? So if that is true, then it means that a times a times ellipsis a, x times is what we have in the numerator, and in the denominator what we have is a times a times a times ellipsis a, x minus 1 times. That is what you have in denominator. Now if you proceed, you will notice that this numerator is greater than this denominator. The number of a's in the numerator is greater than the number of a's in the denominator by 1a. So I'm going to separate the a's in the numerator into two groups by saying a times a times a times ellipsis a is group 1 that contains x minus times, okay, x minus 1a, then times a. Then all over, I'm going to have here, this in the denominator should be x minus 1, sorry. So I'm going to have in the denominator x, a times a times a times ellipsis a, x minus 1 times, okay. So what I have done in the numerator is to separate the xa's into two groups, x minus 1a and 1a. Take note, x is greater than x minus 1 just by 1a. So that is what I have done here. And if you look at it, this will cancel this. That is, x minus 1a in the numerator will cancel x minus 1a in the denominator, and it will leave us with a, telling you that a raised to power 1 is truly equal to a, and that proves the fourth law. Now let's move over to the fifth law. The fifth law in my class was called the law of negative index. The law of negative index. So let's prove that law quickly. Law number 5. So we call it the law of negative index. So what was this law stated to be? It was a raised to power minus x is equal to 1 over a raised to power x. So how do you go about proving this law, guys? I'm going to start again from left to right. I'm going to start from left to right, and you could also prove this law from right to left, whichever one is easier for you. Both ways are easier. You can prove, after proving this from left to right, you can actually prove it from right to left. It's easy. Okay? Now, if you want to get that done, I'm going to prove it two ways. So let's start with the first method. Let's say I want to prove from left to right, or from right to left, a minus x, my left. Okay? So if I want to prove from left to right, I'm going to start with saying that a raised to power minus x can be written as a raised to power 0 minus x. That is the first step I'll take. Now, taking this step means that I can now go to the next step. I can now go to the next step by saying a raised to power 0 minus x, using the subtraction law, is a raised to power 0 divided by a raised to power x. And that would mean that I could have a raised to power x, a raised to power 0 divided by a raised to power x. But remember, we had shown that a raised to power 0, anything raised to power 0 is 1. So this will give me 1 over a raised to power x. So that is the proof from the left to right. If I choose to prove from the right to left, I could say, I could move from this, from right now to left, as 1 over a raised to power x is the same thing as a raised to power 0, which is 1 all over a raised to power x. And the 0 divided by a raised to power x, which can also, by the subtraction law, be written as a raised to power 0 minus x. And this a raised to power 0 minus x is minus x. So whichever way you want to go, whether from left hand side to right hand side or from right hand side to left hand side, this law is true. Now let's move over to the sixth law, the law of powers of powers. That was what I called it in my lecture on indices in the first class. So please go over that video again for learning sake, please, for learning sake. So a raised to power x in bracket raised to power y is equal to a raised to power xy. This law, I called it the law of powers of powers. Okay, so that was what I call this law. Now, how do we prove this law? I could start with saying a raised to power x raised to power y is the same as a raised to power x times a raised to power x times a raised to power x times ellipses times a raised to power x for y times, if you follow what we've been doing. So this multiply a raised to power x or raised to power y means multiplying a raised to power x by itself y times. Okay, and that would mean if you do that by indices also, by the first law, the addition law, remember once you have a number in index form multiplying itself a number of times, the powers will add up. So this will be x plus x plus x plus ellipses plus x. How many times? You guessed it right, y times. Now take a look at these guys. If I told you to add 5 plus 5 plus 5, your answer will be 15. Won't it be the same thing as saying 3 times 5? Of course, it is the same thing. Because if you are adding 5 to itself 3 times to give 15, the answer is the same as multiplying 5, one of the 5s, by 3. So if you are adding x, y times, the answer you get is the same as multiplying x by y. And that shows you that this law of powers is true. And that proves law number 6. Now, I'm going to move over to law number 8. I'm going to move over to law number 8 and then come back to law number 7. If you followed my class on indices. So please, I'm going to put the link in the description below. The law number 8 was called the law of shared powers. I called it the law of shared powers. And those of you who attended my class online on this particular law, I made it clear to you that this law can be compared to how you answer your surname. So you can be 3 siblings answering the same surname. So if you are 2 siblings, A and B, answering the same surname, let's say Charles Okon, Effiong Okon, or Charles Okon and Vivian Okon, take note that the law is saying that each of you have that surname. So what I'm saying in essence is, if you want to prove this law, then let's prove it in this manner. AB raised to power x is the same as multiplying AB by itself, multiplying AB by itself, how many times? X times. Okay? X times. So if you multiply AB by itself x times, that is what you are going to get. Okay? Now, that being said, the next thing to do in proving this law, is once you get this done, you will now have to decompose each of these A times B, like I said earlier on, when it wasn't clear. Now that it is clear, let me re-explain. I'm saying that we want to prove this law, the law of shared powers. Now, if you want to prove this law, you can prove it in this manner. AB raised to the power x means multiplying AB by itself x times, like we've done previously. And each of the ABs can be written as A times B, A times B, A times B, times ellipsis times A times B, x times. Okay? Now, the next thing you can do is, taking like terms, you can group all the A's together. If you group all the A's together, you are going to have this. You have x times, that is A, x times in one group, and you have B, x times in the other group. You are going to have B, x times in the other group. And that would mean A raised to the power x times B raised to the power x, which can be written as AX BX. Okay? So that proves this law to be true, the law of shared powers. Now, if you had attended my class online on the law of shared powers, you will remember I told you that this law is applicable to both multiplication within the bracket and division within the bracket. So let's do something similar for division. Let's do something similar for division. So for division, let's do something similar. Okay? So for division, okay, now let's consider the second case. The second case is the case of division, where you have A over B raised to the power x equals A over B, A raised to the power x and B raised to the power x. So if you want to prove this law, this is still the law of shared powers. If you want to prove this law, then to go about it is the same thing. You could do this. So I'm going to put A over B times A over B times A over B times ellipsis A over B. Okay? How many times have I multiplied A over B? X times. Now, the next thing you could do is to now separate. I could separate them as A times A times A times ellipsis A for all the A's in the numerator. For all the A's in the numerator, I could do this X times all over. For all the A's in the denominator, I could compress all of them by doing this. Okay? X times. And that would now mean you have A raised to the power x in the numerator and B raised to the power x in the denominator, and this law is true. So what we did was A over B raised to the power x is the same as multiplying A over B by itself x times. So we started with doing that. The next thing we now did was to group all the A's. A times A times A times A will multiply itself x times. All over B times B times B times B will multiply itself x times. And that means, by our notation, A multiplying itself x times gives you A raised to the power x, and B multiplying itself x times gives you B raised to the power x, which is what the law is saying. So the law is true. This is the 8th law we proved in my class. Now, the next law I would want us to prove is the 7th law. So let's go back to the 7th law we skipped earlier on. So what is the 7th law all about? If you watched my video and attended a class on indices, you will know that the 7th law was what I call the laws of fractional index. The laws of fractional index. Okay? So the laws of fractional index, they were actually two. One of them was A raised to the power y equals A raised to the power 1 over y equals the white root of A. Now, why is this law called the law of fractional index? You will notice that the power or index or exponent or logarithm, as we called it in the previous class, actually is a fraction. The second version of this law says that A raised to the power x over y is equal to the white root of A, all raised to the power of x. Now, according to this law, you could use deductive reasoning or deduction. So, looking at this law, to prove this, a raised to power 1 over y equals the wide root of a. Now, I told you that a raised to power 1, take note, is a. A raised to power 1 can be written as a raised to power 1 over 1. So a raised to power 1 over 2 is what we denote as the root of a, the square root of a. Now, if you proceed in that manner, a raised to power 1 over 3 would be the third root of a. Okay? And why is that so? Please take note. The square root of a number is one single number that will multiply itself to give a. So if I'm looking for the square root of a, it means I'm looking for two numbers that are the same that will multiply themselves to give a. So the two numbers are clearly a raised to the power half times a raised to the power half. So if you proceed along this direction, then a raised to the power 1 over y can be written as the wide root of a. So let's assume that the number in question is the number being looked at is a raised to the power half. Looking at it, a raised to the power half times a raised to the power half by the addition law will give you a raised to the power half plus half, and that will give you a raised to the power 1. Now, if you go by that that ideology that the square root of a is one number that multiplies itself to give a, and that number is a raised to the power half, then it means that the cube root of a is one number that multiplies itself 3 times to give you a. So let's see, a raised to the power 3 times a raised to the power 3 times a raised to the power 1 over 3 will give you a raised to the power 1 over 3 plus 1 over 3 plus 1 over 3. And that would mean a raised to the power 3 over 3, which is a raised to the power 1, which is a. So that law is true. By deduction, this is also true, that a raised to the power 1 over y times a raised to the power 1 over y times a raised to the power 1 over y times a raised to the power 1 over y for y times will give you a raised to the power 1 over y times 1 over y, and that would mean a raised to the power 1, which is itself a. So this law is actually true. Now, because this law is true, means that the next part of this law, the B part of this law, is also true. And what is the B part saying? The B part is saying a raised to the power x over y is equal to the wide root of a raised to the power x. So is this law true? The answer is a big yes, it is true. So I'm going to use the law of powers to separate this into this. This is what I'm going to do. So I've used the law of powers to separate that, and I'm going to say a raised to the power 1 over y times a raised to the power 1 over y times a raised to the power 1 over y times ellipsis times a raised to the power 1 over y multiplied by itself x times. And that would mean that a raised to the power 1 over y, we have written it as the wide root of a times the wide root of a for the second one times the wide root of a for the third one times ellipsis times the wide root of a for the last one, all multiplying themselves x times. And this would mean if you multiply a thing by itself x times, it means you should have that thing all raised to power x. So that law is true. For those of you who watch this video from start to finish, probably you joined late, you could go over it again from start to finish. And please feel free to ask any question you do not really understand. Ask questions on things you do not really understand. And please endeavor to share this video to your colleagues. Tell them in this class we proved all the laws of indices. Until some other time, if there is no question, if you have a question, please feel free to ask me right away. But in the absence of any question, I'll be ending this video. In my third and final class on indices, I'll be solving questions generally on indices, and that will be tomorrow's class. After this class, I'll be going into logarithm and swords. Okay, so thank you very much for joining this class. God bless you. Good night.